Swayam Prabha. Digital India. Educated India.
Good morning, students. We have been discussing this application of impulse momentum equation for a few typical cases. As we said, as such, it doesn't offer too much of an advantage compared to the direct application of the dynamic equation. But on the other hand, there are certain situations where the impulsive forces are very, very large but acting for a short time. So, which are called impact. So, where the real application is when the forces are large and duration T2 minus T1, which we call it T, is 1. So, we would like to take some applications where the forces are large, but then they act for a very short time. So, we have several examples of this impact, such as particularly, obviously, the forces are the internal forces, or the forces acting from one body to another body. So, one of the applications which you might have seen is the impact between bodies. So, for example, a simple example, impact between collision, you call it, or maybe collision is a right word. Collision. So, in the sense that if you have a body here and the body here, this is A and B. So, for the sake of simplicity, we take them moving in the same direction. So, if BA is greater than BP by, then at some point they will touch each other, and at this point, so there is a large force so there is a large force act here, and the force is quite large compared to large in the sense that there are other forces like compared to the weight WA and WB. So, these forces F are very, very large. So, anyway, so if you want to apply our impulse momentum equation in a graphical form, so this is at time t1, and during time t1 to t2, which is very, very small, so if you want to apply that equation, obviously you have to integrate it over time, right? Everything. One to two, everything is T1 to T2. So this now equal to, so they will be moving with some other velocities B prime. Of course, if you want to make the equation, so then obviously they should be multiplied with masses so that it will become momentum, linear momentum. So this is exactly the equation which we have studied in our last class, but now we are applying it to two bodies. So how do we apply that here? So the problem here is that the F here is not known. Okay, earlier in the simple examples of ball rolling, we simply said that F can be just equal to mu times n, but it's not so here. So F is an unknown quantity, and that's where the real application of this impulse momentum comes into the picture. So one of the things that the first equation can be applied here. So if you have the balance in the x direction, so we will apply it for both the bodies together. Okay, right? We can also apply for both the bodies together, right? That we can always do. So even earlier also we can apply the equilibrium of forces for one body or even two bodies together, right? So here also we'll do the same thing. So what we do is that MAVA plus MBVB. Okay, so plus, the interesting part here in the x direction, we have minus f dt and plus f dt, which cancel. I'll just write it here. I write it here just for the sake of completeness. And this is equal to the MAVA prime okay. So this even simplifies if you just remove that, simplifies as well, this is quite well known principle. So what he says is that the linear momentum before impact, okay, is equal to the linear momentum after impact. So the linear momentum is conserved. So this is conservation of linear momentum. So a simple question in our last problem of a ball being put on the ground. So is there a conservation of linear momentum? No. Okay, because for example, to start with, in the second case, so it's just angular momentum, and then the ball is placed, and then it gained linear momentum because of the friction force. So there's no question of conservation of linear momentum. Okay, so this is one thing. And apart from this, so we need we have two unknowns here, VA prime and VB prime, and then to calculate these things we need one more equation. So what is that equation? So there's one more equation here. From understanding from the nature of collision. Nature of collision. Okay. And so that means that what kind of interaction that takes place between these two bodies at the time of collision. And these things, depending upon the type of material you have, so the collision may be purely elastic, to all the way to purely plastic. And here imperfect or inelastic collision. Okay, it's purely plastic to inelastic, partly plastic, okay, and purely plastic. So what is the difference between these two? So purely plastic means the deformation that takes place here is completely regained, and so just a purely elastic body, right? If you apply force and some deformation takes place, and that deformation is completely recovered once the force is removed. So the complete recovery of that is because the material is behaving like purely plastic. Whereas on the other hand, at the extreme end, so purely plastic means that if you apply a force, if the deformation takes place, so let's imagine that it becomes flat, and then even if the force is removed, it doesn't regain its circular shape. It just that deformation stays there. Okay, so that's purely plastic, and somewhere in between it is also elastic plastic kind of collision. So what is the then, if you go to these two extremes, so what is the kinematics that are affected by the kind of material behavior? So in the purely plastic elastic case, so whatever deformation that takes place, so that is completely recovered, and then the energy that is gone in there to deform it is completely recovered. So that means that whatever energy is there, it is not lost. So a conservation of energy applies here. In this case here, purely elastic, so conservation of energy applies here because there is no energy loss. So here the energy is completely lost, so there is no deformation. So that means that if two bodies are coming and colliding, so they get deformed, and then there is no recovery that takes place. After the maximum deformation, neither this recovers nor this recovers. So that means that they stay like that only at the maximum deformation status. Okay, the maximum deformation. So what does that mean? So here in the purely plastic case, so the bodies are at the point of contact. At the point of contact, remain together. So this is another thing. So that means that in the one end they are completely recovered, and then the energy is applied, and whereas when there is a plastic impact is there, so there is no recovery of the deformation, and at that point the bodies remain in contact. So obviously you can see that when the deformation is retained there, then the energy is lost. In this case, conservation of energy applies, so there is no energy is lost. Okay, energy is lost. Obviously, there is no conservation of energy. So either the additional equation either come from this one. So if it is a purely elastic case, so in this case, so then what is the equation? So it is half MAVA square of B square Of course, here we are assuming two things, that the bodies are very small and then it's only a linear motion, right? Bodies are very small, smooth and circular. So this kind of impact is called the central impact. The G and G1, GA and GB are the collision is taking place here along the line of GA and GB, right? So, and then when they separate out together also, the velocities remain in the same direction, AB, right? Whereas if you have a larger body of not necessarily of circular in nature, some other shape, then there's a possibility that once they hit, then they may go in some other direction depending upon the shape. Okay, so for example, if it is coming and hitting, so it's possible that they may go in some other direction, or also it may include the some kind of rotation. So that also we will see just now. So just to conclude this one, so this is this, okay, for elastic impact, this is the additional equation. And what about the plastic impact? What is the thing? So that means that at that point they stay together, they will have the stay together means stay together relative to each other, okay, not that they'll come to a zero deformation, I mean zero velocity. No, it's not completely like that. So relative to each other, they are in contact. So what does that mean? So that means that here the velocities here of A and B, so they become same. Okay, somewhere in between, so there is some kind of other possibilities are there between these two. In fact, there is some theories are there. There's some, so how much is required and how much is not required based on some other parameter known as coefficient of restitution E. So that is also brought into the picture. So we don't go into that. So that's not our. So this is as far as this is concerned. Just now you can definitely solve. I'll leave it to you. I think anyway your earlier course on dynamics. So obviously you have seen this kind of collisions, central impact kind of collisions, and can apply this. The bodies having size and shape. So we consider them as not a rigid body, but of course we make use that there is a collision that is taking place and the deformations are there, but maybe very small compared to the total size and shape of the thing. So one another important application, another example here. So here we have body, size and shape. So one example which we take here is that a square, a block, a rectangular block. Is moving on ground, okay, with a uniform velocity. V and V naught, and encounters a very small obstacle. Okay, and our interest is to find out what happens immediately after this collision. What happens after? Okay, so what we mean here is that we have a block here. We have a block here, and then moving with velocity v naught, and encounters a small obstacle here. So, and then finally what happens? So the body will be so you can see here. So it's coming with this kind of thing, and this G here okay. So what's happening here is that this is coming and hitting this one, and then this is going to topple. Okay, going to topple here, and about this is the important point here. So at A, it's going to about A, it's going to topple. So there are several cases here. So let us see if you want to put it as an equation here in a graphical form. So what we have here, this is mv naught, okay, purely moving down the horizontal floor, and then here we have, if you want to remove the obstacle, so we have here so there is n dt here, So we have two forces here, large forces. Let's put this as FA Y, and this. There's another force here, and so this is linear momentum, and then this is the impulses, and here we have, I put down the velocities, but we can also multiply with mass here. Okay, so this is the complete graphical equation where we have the things to start with at instant 1 and at instant 2 here, and something happened between T1 and T2. In fact, you can also see that the T1 to T2 is a very small time here. The whole collision or the impact takes place over extremely small time. But however, the forces that come here, and if they are integrated with time T1 to T2, now the time duration is very, very small. Delta T almost tending to 0, very, very small value at delta. And so you can even assume that FA is very, very small. In fact, you can even write this as FA times delta T, and this also. So what essentially here we Fx and Fy, we don't know. We can even assume that they are uniform, but essentially we are interested in the total integral value of Fy delta T. Sorry, this is y. Okay, so this is what we want, and this W delta T also we can write it as W delta T. Okay, so if you look at this equation, we can formulate, we can make the equations, but our final interest is to find out what are the values of, what is that, this Vgx and Vgy prime and omega prime. So this is the three quantities, and as usual the number of equations which you get here will be 3, and then the unknowns are how many? Lot more unknowns, Vgx and Vgy omega prime, okay, as well as Fx and Fy, okay, which are there. Okay, so how do we make the equation? One of the thing, before going into the nature of collision, so one of the things which we can put here is this is immediately after impact, okay, that's what we are saying here. In fact, this is started rotating, but the configuration here has not changed much. Okay, so it started, the velocities have changed, but the geometric configuration is still horizontal only. Though I have shown it that it has shifted here, but you can assume that it is still in the horizontal position. Okay, so what we have here, we can go through the whole procedure of making the balance equation in the x direction, balance equation in the y direction, and the momentum equation, and then the nature of the impact here. So what is the impact here? Impact at the front or so this is again two types here. Let's take the plastic impact. We will take the elastic impact just now, but let us start with plastic impact because that is a simpler thing. Okay. So what we would like to do is that to make the equations, so this f, let's also say that this fax delta t fax and fay are very large and delta t is small. However, fax delta t and fay delta t are finite. That's important. They are neither small, okay, delta t is small, so that means that this is not small, neither is it very large. So together it is something finite, okay, so something finite only. So now let us see one of the equations. You can make all the equations about G and all that, so let's not do that. Let's directly go to taking the equation, moment equation, which we are going to, so we directly use moment equation about point A, A. So what is the advantage of taking the equations about A is that the large values here, the impulses, okay, impulse of the impact forces here at A, they will have zero moment, okay, while and further this W times delta T, which we write here, what is the magnitude of this W delta T? Is delta T is very small, but W is finite. So that means that W times delta T is very, very small, okay, while saying that Fay delta T and Fax delta T are finite in nature, this W delta T, so let's see, delta T is very, very small compared to Fax delta T, or so this is negligible. That's what you have to understand. So if that is the case, then taking the moments about A, so what we have here, mv naught b by 2, and this is all 0. And here we have an interesting thing here is that mvgx prime times b by 2 mvgy times a by 2, right, plus ig times omega prime. Okay, so this is what essentially I have to do, but the G is put as vgx and vgy prime, but on the other hand we can simplify this equation by understanding that this is a plastic impact, so we have to put the constraint that the point A is having a plastic impact. So let's just do that. What does that mean? Plastic impact at A. So as we said there, so if it is a plastic impact, then the points where the plastic impact is taking place, okay, will be deformed to such an extent, and then they don't require the deformation, and they stay together, okay, they stay together after the impact, which means that they move at the same velocity, or if you know the velocity of one of the body, then you can say that the same velocity holds good for the other body also. So here we know that it is a ground against which the corner A is impacting. So we can say that the VA point A on the body okay will become 0. Velocity will become 0. Will become 0 after impact. Okay, because they should have the same velocity after impact. So since the ground is obviously having a 0 velocity, so the corner A of the body also will come to a 0 velocity after the impact. So what does that mean? So that means that the VA prime will be 0. So this means that VA prime is 0. So now let's look at this one. So this point here is coming to a rest here. So if that is coming to a rest, so which means that V prime AX, both V prime AY are 0. Okay. So that's what we have to write. So which means that VA essentially is 0. So which means that we can formulate the velocity equation for A prime as Vg prime plus omega k cross equation vector of A with G. Okay. So we can say that VA prime X I okay. A with G. So that means that G is the reference point. A with G is what? So it's A by 2I minus B by 2J. Okay. So let's look at this, simplify this further, which means that, so what is that which we need? So VAX is VG x prime. So we are taking the ith component, and k cross I is k cross j. So it is omega prime b by 2. And v prime y is v prime dy So which means that if this had to be 0, right, Vax and Vay had to be 0 separately, and so therefore Vjx prime is minus omega prime b by 2, Vgv prime is minus omega prime a by 2. So these are now the two constraint equations which have come from the knowledge that point A is coming to rest after the impact, and so using that, so we have Vjx and Vjy like this one, so which you can make use of Euler equation. So we have Euler equation 1, and this is 2 and 3. So we can substitute 2 and 3 in 1, and 2 and 3 into 1. So what we get? Mv naught by 2 is equal to V prime Gx. So V prime Gx is minus omega prime V by 2, V by 2, and here Vgy is minus omega prime A by 2, A by 2, and then this. So in this equation now you can see that we have only omega prime, and that's the only unknown, so you can take it out, and if you want we can take it out as omega prime can be taken out, so it's 1/4 mv square, 1/4 ma square. So only thing here is that when you make these equations, so in fact when you make this equation, this product, cross product equation, so here this omega prime is assumed to be counterclockwise. Okay, so this is counterclockwise omega prime, but if it has to be in consonance with this one, so it should be negative, and it should be negative here, okay, and positive here, so which means that these things will become positive, I hope. So this omega prime here is taken as a clockwise, but in this equation whenever we do this one, this is counterclockwise is actually the positive part. So you can see that in fact the one in the square bracket here, Ig plus 1/4 ma square 1/4 mb square is nothing but the inertia of the rectangular plate about A itself. Okay, so this is the elastic impact about point A. Okay, in fact here also we said many times, so we can even find out the G, okay, G from A. Okay, if you want to go from G to A, it's also possible if it is going from formulating the equation G with respect to A, so which means that you have Vg prime in the sense that, so we know that the point A is stationary, so which means that the whole thing will be rotating about A. Okay, if this is rotating about A, so that means that if this is omega, this is omega prime minus d by 2. D is the diagonal. Okay. So in fact, if it is A is equal to B is equal to, then this angle will be 45 degrees. So this completely, so the G, very clearly you can see that Vgx prime is nothing but omega prime d by 2 times cos 45 degrees, right? And similarly, okay, you can directly use this one, Vgx and Vgy primes. So directly in terms of omega prime, by knowing that A is the point about which the plate is rotating. So using that, okay, so we can directly write the constraint equation. Okay, if the impact is elastic, if the impact is elastic, so what will it change? If it is impact is elastic, what are the things that are going to change? One is, of course, this. So what we have here is that the point A in the corner is now not going to stick, and then it is going to rebound. So if you take this one, point A here, the point A here is going to have a rebound. Will rebound. Okay. So, but then this rebounding is of a certain nature. So that means that if this is what's going to take place, so this is after so if A is going to rebound, so there is a ground here, and if this point A is going to rebound, then what it can do, it has a certain restriction. So it cannot really penetrate, right, because there is a ground, and then there is no vertical motion for A, but only the motion it can have horizontal motion, only in horizontal direction, because it cannot go into the ground, nor will it leave, it will not go in the vertical direction upwards. So it only tries to penetrate if possible, because this is going to rotate and then A is going to penetrate into the ground, and that will not take place because this is a hard ground and you cannot do that. So essentially, so that means that VA prime here is horizontal, or what is that which we can say? So VA prime Y is 0. This is one constraint, right? This is one constraint. And what else? So since this is elastic impact, we can also say that elastic impact implies that the energy is conserved. So that means that so the constraint here is Va prime y is 0, which means that V prime x I, put it one step before, V prime can be written as V prime, or even the other way we can put it. Let's just do that. Vg prime is equal to, so this is also is fine. Okay, so we can write Vgx prime, Vgy prime, j, and this is only Vjx prime I, and this will become G with A. Earlier we wrote it A with G, G with A is now minus A by 2I. But as said earlier, omega prime, if you want, we can put it negative, because this is what we assume. So what we can get from this is two equations. So what is that we can get? So Vgx is V prime Ax, right? And A minus plus, this is what Vgx, and Vgy, V prime Gy is simply A by omega prime A by 2. So these are the two constraint equations. Okay, so where we have been able to express Vgx and V prime Gy in terms of V prime Ex. Okay, so these things are taken care. So what is the other equation which comes into the picture? So the other equation is because of this nature of collision, which is the elastic, so where we do not lose energy. Okay, so if it is an elastic impact, so we don't lose any energy, so we can also do. So one more equation is and conservation of energy. Okay, we have the unknowns are V prime X and omega prime, and so we have the moment of momentum equation about A, you can still apply. So that is one equation together with the conservation of energy. So you will be able to solve this problem. Okay, so finally, since you have, interestingly, since you have the energy equation in terms of the quadratic, the second power of Vgx, V prime Gx and V prime Gy, so we'll end up with two solutions, so a positive solution and a negative solution. So that's important here. So you can calculate V prime Ax out of that. So V prime Ax, so what is that? So one is, if you look at here, V prime Ax, one will be in this direction, one will be in this direction. So obviously, since it cannot penetrate, so you can ignore this solution, and you have to ignore the solution which is rebounding, okay, which is going in the leftward direction. Okay, in fact, we even assume that it is already in this direction, and no, we didn't. So appropriately, you have to take the solution V prime Ax when you solve, so which is moving in the direction leftward. Okay, so this is the algebra involved is a little bit involved. So let me give the final solution for you. So let's assume the data, assuming A is equal to 1 is equal to B, and where the diagonal will become root 2 and mass is 1. If you use that, so you get VA prime and omega prime as so we have two solutions for VA prime. I mean, we have VG prime from which we can calculate VA also. So in which case what happens is that VA prime is negative 0.9601 and omega prime for 0.6, and the other solution is 2.264 and 2.45. Okay, so the solution is that a positive thing is not acceptable because it cannot penetrate. Okay, so that means that this is wrong. A cannot move to the right. Okay, so that way we'll take it to be negative. So the correct solution is so VA prime is nice. Okay, so this is some meters per second, and so this is the solution. Okay, so I hope you got it. So this is the difference between plastic impact. In the case of plastic impact, which turns out to be a little simpler, is the point A suddenly becomes stuck and the body rotates about A, whereas in the case of elastic impact, the point A rebounds, but its velocity after impact is horizontal only because it cannot penetrate the ground. So it has to move horizontally backwards, maybe, if you want. Obviously that's what we did. You can assume it to be positive, and then final solution should be negative. And then we connected G, we wrote it in terms of A, and so similarly, since VA is still there, so we require one more equation, which is the conservation of energy. So then you solve it, and this is the final solution you get. Okay, bye bye then.